code and do some TCP stuff with you today. So we had a look at UDP, and we talked a little bit about Indians and those sort of things. And so we're going to talk a wee bit about sort of more game stuff and how games on internet actually operate and some of the challenges. Right, so if we have a look last time, so we were starting talking about game models and a server-client model on networking, and you can imagine that this middle piece with the cloud, we have firewalls and peer-to-peer communication. If you've got a server and everybody knows its IP address, then it's pretty easy to get to that IP address. However, when you're all behind a firewall, you need to do some specialist stuff to get to your computer, right? So how many of you at home have a firewall on your router? Pretty much everyone has a firewall. Have you configured your firewall to serve to become a game server for anything? 1, 2, right? Maybe. Where you go in and you actually say, oh, I want to expose this port, right, this local address number on my machine, to the outside world, right? And so when the outside world communicates to your router then takes that message on a particular port and sends it through to you, right? And then you can host that game. Now, one of the challenges of that is that if you have, like most internet services in Norway don't guarantee you a static IP address. Right? Do any of you pay for a static IP address? You can ask. I think IDSever is charging like 25 kroner a month. Free if you asked enough. so you have to ask, oh, right. So I was thinking I can't stream because...
Oh, I got your gear.
Right, I got the gear. So I'm streaming on Simon McCallum rather than GTL.
Because we cannot stream together.
Because you can't stream from two GTLs simultaneously, because our GTL can't be live YouTubing, and he was already streaming in the room. So I put it on Simon McCallum. So if you could tell them, any live streaming person at the moment, to go and have a look. So if you put a link up into the Simon McCallum one, they can watch live, and it will be recorded, then they'll move it over into GTL later. Yeah. Okay, it's just that we had simultaneous, and I was looking at it going, it doesn't let you have two live streams from the one YouTube account.
Same account. Yeah, exactly.
At the same time.
Doesn't usually happen, but
No, we usually aren't trying to do quite that the same way. Right, so with a static IP address, right, so one of the things about having a static IP address is that if you have a range of addresses, right, so if you're Altibox and you have 16,000 IP addresses that you can allocate, right, you might have, 17,000 customers, right? And if you're at that point, you're going to have to dynamically reallocating those IP addresses, right? Now, and partly because we've run out of IP version 4, so your standard IP addresses you see, which is 4 numbers, right, which are each a byte, 8 bits, each of them. We've now run out of internet addresses. No, we don't actually have enough internet addresses in the world for all of the machines that want to be on the internet. No? And so a lot of your machines, so your machines at home, they go through a router. They don't have their own internet address, they don't have their own IP address, they have a local net IP address, right, just locally, but to the world, they look like your router. Right? So all, like your phone and your PC and your girlfriend's phone, all of them to the internet look like they're one machine with one IP address, all sending data out. Right? Because it can't see any of the internal addresses, because your machines don't have internal static addresses. Right? They actually have dynamically allocated address by your router in your home, will allocate your local addresses in your local address space, and everything will look like one address on the outside. Which is why our Heroku install got crushed, because all of you guys going through eduroam are going through a proxy, and so to the outside world, you'll look like one address. And so for Heroku, it goes, oh my God, you guys are hammering, you as an individual computer are hammering us. We can't let you do that, right? If you're all individuals, and it was actually, if you had your own IP addresses, it would go, oh, there's just a lot of individual students hitting us, 1 or 2 times a day, that's fine, right? But when one machine is hitting you hundreds of times, you think, that's someone commercially doing work, because they set up this constant, almost denial of service attack look of constantly attacking us. They can't be using the service normally because you wouldn't normally make that many requests from one machine, right? But you all look like one machine because you're behind a proxy, which you all go through, and that's your IP address, right? So the world sees you as an MTNU proxy. Well, not really, because you're a single point attack, right? So to DDoS, you'd actually all need to be spread out, and so you all go home and use your home internets, and then all come in, right? So we're actually the opposite of DDoS, right? You had a single point of attack, right? So peer-to-peer, one of the challenges is being behind a firewall and being behind this router address, right? So when I try and find your home computer, if you tell me if you do an IP on your home computer, it will give you a crazy number, which is your local number, right? So if you do IP config, how many of you done IP config on your machine before? Yes, we've got IP config, yay! That tells you your local, it'll give you a local address. It'll also give your router's address, right? Luckily, because it can ask the router, oh, what's my address to the outside world? But that will only get people as far as your router. Because to get to you, they need to know your subnet address. And so when you're writing up, so if you're trying to create your own server for a game, or to serve a web page out, you need to tell your router, redirect, if it's a web page, port 80 to this local machine with this port. And then you could start serving. But then at midnight, your internet provider shuts down your internet and starts it up again with a different IP address, and your website's now gone because no one can get to that IP address because it now belongs to someone else. Right? Which is why you pay the 25 kroner a month to say, no. When I have this address, I want it to be that address all the time. So that when someone types in ntnu.no, they go to a specific IP address because that's in the lookup tables, right? Because, when you type stuff in, there's a big DNS lookup table where it actually goes and finds all those addresses. Right? And if your address changes and you don't update all of those tables, your system is lost.
Did you generate a new key for your stream?
Did I generate a new key for my stream?
I don't think so. Because
Oh.
I'm streaming here.
I'm streaming there as well.
No, you overstreamed my stream.
I overstreamed your stream. Oops.
So I lost my stream.
Oh, sorry. I did stop streaming and then go into my account and come up in my account
Yeah,
and then
but you
start.
generated a you have to attach
Ah.
the new streaming key
Oh, okay, maybe not.
in OBS. Yeah.
Okay, okay, so my OBS is actually streaming. Okay, sorry. We'll just continue. We'll have to work out how that works. Sorry, the end of your course.
For this class is fine.
Yeah, you guys. I trampled over his stream, so you guys are fine. His other students are missing out. So we're going to look at the client-server models, and we're going to have a look at some of how these IP works, and we're going to look at a little bit of TCP/IP, right? So as I said, that lookup and that IP number, you have to have a known address. Now, what we're going to look at with the client-server models, how do you deal with being behind, right? So we know that it takes time to get somewhere and get back. So the world state, the cloud state, is different to my local state. So there's lots of things in networking where you have to do prediction and you do predictive caching. So you have to understand who owns the true world state and how you hand over in the cloud between one machine and another machine. Right? So we'll get back to the networking and the IP addresses in a minute, but we'll talk about these world states. So if you've got a database on the cloud, right? So you guys have used, I'm going to use cloud database service, right? So even like Google Sheets is a cloud service. So you're using a cloud service. That will be hosted on a machine somewhere. Now, load balancing might say, oh, actually, I've replicated that in multiple places so that, you know, when I travel to Spain and I go on the cloud, I can get, instead of going all the way to Norway to get my data, I use the closest replication to me. Right? So it replicates it in the cloud and tries to make it transparent to you. So you attach to one service and it goes and finds that. However, to copy that data to a server close to me on the cloud, I have to hand over information. So I go from one server where it's got one set of data to another server, and I've got to switch the internal routing information. So you hit in one point, right? So imagine this is your home network. You've got one output that is from your home to the world. And you're going to move a file from being stored on your computer to being stored on your big set of network drive space, right? So you've got your computer here, you've got your network drive, and someone's using it from outside. Right? So they're outside, and they just see your front door and your data or your stream coming out your router. One thing you can do is you can copy it across from your machine onto your big rack of storage. So you copy the data across, and then in one instance, you do a quick redirect saying, okay, I'm going to change the pointer. I'm going to change the table that tells you how to get that data. So I'm going to go from pointing to machine to blink, pointing to the big network rack. Right? So that is a lookup table in your router. You do one change and one packet goes there and the next packet comes in and goes straight over there. Now, the challenge for the cloud is partly, what if this packet changed something in the database? So I've already copied it across, right? I copied the file from here over to this other location. And then you change it there with one packet. The next packet you send, I redirect with my one switch in my table over to here. What happens to that? Do I lose that update? Do I cache that update? Do I stop the network and buffer everything while I copy? Because I say, you're not allowed to touch it while I copy that massive file across. But you know, if it's a big database, that might be several minutes while I copy it from one location to another. So do I lock you out? Do I give you partial access? Do I take that access and when I move it, I record all of those interactions between you and the database in the time that I'm copying? So I kind of make a local copy, let you start editing that, record all the changes to it, copy the big mass across, then look at all those change sets, and then take that, copy that across and do the update with that, and then look at how much has happened since I did that, and iteratively get a smaller and smaller change set of what you've been doing, and then finally get the last one across, and then flip you so you don't lose any data. Right? Now that's what you guys are doing in Git, right? When you do Git, you're making change sets. You edit a file, you upload it, it's got some changes. So this is one thing they do when they're actually on the server, is you copy large chunks to replicate a database, but you have all these change sets. And what databases are really good at is they're good at actually remembering the changes. Right? So you actually have those transactions. So you guys are doing databases at the moment? So you've been doing some transaction analysis, you've talked about... Right, okay. So the way in which a database state changes, right? So you actually have rules, relational algebra, that tell you what's a legal change in a database, right? So basically what you have to do is you copy the content of the database, and then you can copy all the changes since you last started copying. And then you can copy those across and update the new database, right? So you've got this server migration challenge. And handing over with multiple objects. I don't know if any of you are gamers, but as a gamer, I assume some of you are. When I was playing Diablo, the first version, back in the day, one of the hacks we had was that if you walked into a teleport back to the village and dropped an object after you'd entered the teleport, but before it had copied you, before it moved you, the object would be dropped into the world and remain in your inventory. Right? Because the timing of how you hand over data from one pass to another, it started the inventory, so it did the copy it into the world before it got round to doing the inventory check, and by the time it did the inventory check, you were already gone, and so the object had been copied into the world and had remained in your inventory. So you then go back through the teleport and pick up the second version of that object.
There's a similar image I used built in Pokemon second generation.
Yes.
Pokemon second generation.
Where you basically just put your Pokemon in a PC storage, start saving, and then basically shut down your system. So
Right.
It saves that it's in the computer, but you still have it in your inventory.
Because it hadn't got round to the point of deleting it from your inventory. Yep. So
Trading as well.
yeah. So this server migration, gamers will find your flaw in your algorithm for how you do server migration, right?
It's not cheating if it's in the game.
If it's in the game, it's in the game. So this is a big problem with databases. How you avoid like those replication errors. How do you keep all of your duplicated cloud database up to date, right? This is a big, significant challenge, and there's lots of these change sets that you need to understand, and the communication protocols of storing those changes and reapplying them. So, the firewalls. So one of the things that we do with those network addresses is to do firewalls which prevent people scanning your machine, right? So back in the day when we didn't use firewalls, you connected your machine to the internet, and then any open port was open. And so the people would be able to port scan you. And to port scan, what you'd do is you'd find someone's IP address, and you'd start sending messages to port 80, port 81, port 82, port 83, port 84, port 85. You just spam all of their ports to see if any of the ports responded with anything, which means something was listening. Some program was listening. And then you try and work out what that program was, and then you try and break in through that program. Right? So that was port scanning. So your machine, as soon as any program started running, it would open up a hole that someone could come in through. With your firewall, that's why whenever I run the client thing, it pops up, the wee firewall says, oh, you're trying to open up a port. Do you want that to happen? So the firewall software is looking at it saying, no, I locked down everything. Oh, you've requested to open one? I better ask the user if that's what they actually want. Right? So a firewall tries to prevent you doing that. Now the firewall here on campus is run by IT. They decide whether or not you're allowed access. Right? So if you want to open up another port, we were looking at doing networking between here and Lillehammer for a game on a port. And so we had to ask IT to open that port on the firewall from us and on the firewall in Lillehammer, so that our game could talk directly to each other on that particular port for its networking, right? So it'd have direct communication rather than having to go through port 80 to a server somewhere and then come back through port 80, which the firewall for port 80 is open, right? So rather than having a server S mediating everything, they just mediate the initial connection, work out what the firewall, what your port settings are, and then communicate. So we were doing peer-to-peer, without a server. So we actually didn't use a mediating server because there was just two, right? So we knew what our IP addresses were both in Lillehammer and here, and we got static IP addresses, so we could just do that directly. And we're looking at setting that up with Trondheim, and Ålesund is setting up in the VR lab, setting up a permanent connection. So we have the wee video feed, so that we have a screen and a camera which is constantly feeding from here to Trondheim and to Ålesund. So you walk into the room and you can see the people in Trondheim or Ålesund and what they're doing. So the labs are kind of single lab, right? So that requires a static. We're going to do it by the static IP addresses and with opening up a port in their firewall. Okay. One of the other things we do with that and the data is called seamless travel. You may have seen this in games. One of the ways of moving data back and forth is is that you try and bring in the new data you want before you need it, right? So you do look ahead. Now you'll find this in web pages. Some of your browsers, your mobile phone browsers, and some of your internet browsers will do look ahead caching. So what they do is when you go to a web page, I think Opera does this, or they were doing this, is that they look at the web page and they know from their statistics of people using their browser which link you're most likely to click on. So what they do is they look at, oh, you're likely to click on that link, so I will prefetch that link for you before you've clicked on it, because, you know, you might want it. So I'll start downloading it now so that by the time you worked out that you wanted to click on that thing, you'll click on it and bang, I'll have the page instantaneously for you. Aren't I much faster than every other web browser? Right? Because it predicts what you might want to do. So in games you can do the same thing where you're walking in an environment. As you start walking towards the door, the game goes, aha! The player is walking towards the door. They're probably going to use the door to go into the other room. How about I prefetch all of the data on my networking from the other room so that when they get to the door they can walk through it and I've already loaded everything they need and I can just keep playing. Or you do the terribly slow thing of they walk to the door and you play a door animation and you block everything and you have a loading bar and you load it and make everybody wait.
Or if you have a bad computer, the loading speed might be better than having 50 FPS.
So if you have a really bad computer, it might be better to optimize your local experience than to start slowing you down by bringing in network packets for something you haven't got to yet. Right? So you're right, one of the challenges here is how do you do that network lookup and pre-calculation and preloading. If you're doing an interactive game and you've got a lot of network traffic, then preloading is going to slow down because it's going to use the same network, right? So you've got one network card. So if you're going to preload a whole bunch of data, suddenly your interactive speeds slow down, right? And so that would be bad. So you'd say if I'm already at about, you know, more than 50% network utilization, don't pre-cache stuff because it will make the experience worse. And so you'd hit the barrier and do that copy.
I think you're going to work at does this when you enter the raid, all the bosses spawn, and everything they're going to drop, that reset for your group will also spawn onto the corpses.
Yep.
So
So yes, they try and if you are going to take the player out, you pre-spawn everything you can in a period where you've got a loading screen, right? So that's part of the network seamless travel. One of the things that we're going to look at when you're networking things is so you have the seamless travel. Part of that is also to minimize the amount of data you send, right? So the same when you're transferring data, you want to always send the minimum you can. And when you're networking, you try and send the minimum data. So there are various optimizations. So one of the ones in, I think that's a Unity one, and in Unreal, they have things like F vector net quantize. And so the idea is you take a floating point vector, right? So you guys have done C++, you know what a vector is? Right? So you have vector of floats. Frodo hasn't taught you vectors?
We're talking like the array vector or an XY vector.
We mean vector as in the standard template library vector. Guys know standard template library vector? Hopefully you will. If you don't, you should learn standard template library vector. Very, very useful. So if you have a vector of floats, yep. So 64. If you've got 64-bit floats, right? That's a massive number to send, right? So we were looking at those bits, the header, and I was saying, you know, 50 bytes in your header. That's ridiculous. But if every float is 64-bit, right? So every float is 8 byte long, right? So 64-bit, so 8 bytes per number. That's an enormous amount of data just to send XYZ, right? So just to send one position, you're using a huge amount. So it uses a function called net quantize, which says, oh, take your floating point number. Instead of being a 64-bit floating point number, However, you make it like a 16-bit floating point number, where I'll lose a lot of precision, but I might not need 64 bits of precision to be copied across the network. So what you do is you crunch it down to a much smaller number that say, well, that's good enough, and I'll send it off, right? So instead of being exactly precise down to a millionth of a millimeter, you might miss or hit just a little bit because it's quantized it, right? It's got rid of a lot of the detail. And so and you can write your own quantize function, which says, okay, take my 64-bit int and just crunch it down into an integer, right? And either a 16-bit int or if you do an 8-bit integer, you've got 0 to 255, right? So you're thinking, I've only got 250 positions I can be in this world, right? Which might be a bit too quantized, right? Because that might make you jump around the world a bit much. But one of the ways you do this is you can say, the last packet I sent you had my XY position in it. How about I just send you the difference between my current position and my new position? And I'll quantize that, because that could be a small number, right? So I don't have to get my world position in. I'm saying, use my old world position and just update this little bit here. Right? You can actually visually see some of that optimization happening in some videos. You'll see you're watching a video and then suddenly you'll lose one of the keyframes, which resets all of the colors to the right colors. And you'll get just the differences. Have you ever seen a video playing and then suddenly all the colors seem wrong and they're like shapes are moving, but they've got the texture of the old shapes? Right? Yes, you've seen that happen? That's because in MPEG what's happening is it's actually in between frames. It's not giving you a full color frame, it's just giving you the difference. The difference between this pixel and what it now is. But if it loses the keyframe, it keeps using the old color image and just doing the small color variant from the old image. And that's a networking issue, right? They're saying, okay, we don't want to have to send RGB. We don't have to send big data every time. So we just send the little differences that are happening per frame. But that requires you every now and again to resynchronize with what's called a keyframe, where you send a big everything frame, and then you send a second of little differences, and then a big frame, and then a second of little differences, right? If you lose the keyframe by a network packet being dropped, you then have this weird mottling effect where you get the old texture.
Will this not give like very stuttering video where you have perfect frame, decayed frame for the decayed frame for the decayed frame, perfect frame for the decayed, like that transition from very decayed frame to perfect frame? Would that give like stuttering?
Well, actually, no, it generally doesn't, right? Because so long as you're getting all the packets, right, you're getting just the deltas, but you're getting all the changes, right?
You're only getting quantized.
You are getting quantized, but you guys aren't good enough to notice that you're getting quantized,
Okay.
right? Your eyes aren't good enough to notice how bad the image is, right? Because your brain averages a bunch of things, right? In fact, JPEGs are all about messing with the image in ways that your brain doesn't recognize.
So there's during the screen only has 3 colors, right? RGB.
Yes.
So brain has to review a lot.
Oh, so much. Yes, your brain messes with you enormously about understanding color, right? But that kind of MPEG compressing is mostly about network traffic, right? And JPEGs, the reason we have JPEG compression is not because we were worried about hard drive space. It was we were worried about sending an image from you to someone else, because if you send a raw image, it takes forever, right? And so you had to find a way of sending small bits of data, right? So a lot of the data compression techniques we have were about this sort of networking, right? And they also means that we do a bunch of really odd bitwise operators.
So, what happens if, like, I've seen very weird collisions in League of Legends where suddenly the auto animation of minions, the graphic is replaced by another icon, and it was really wonky and it won't fix itself.
Right. So that's actually more to do with an issue with the game loading assets and it getting a pointer out, right? Most likely, rather than a bitwise operator. So, but yeah, so the idea is that we're going to minimize things, and we're going to talk bitwise operators and how to compress data. Do you guys know anything about bitwise operators?
We did learn about it. How to use it.
Right. So where did you learn about it?
Discrete mathematics in the first semester.
Discrete mathematics first semester. You did a little bit of bitwise operators.
Yeah, we also, I don't remember the name of the algorithm, but we did go through somewhat the algorithm for compressing JPEGs.
Okay.
Um,
Excellent. Right. Yeah, there is a Fourier transform and shrink and minimize
for
differences.
example, you can't compress a JPEG twice, but you can rotate it 90 degrees and then compress it again, and rotate it 90 degrees back and compress it again. But so you can't do the same operation on the same.
The same data will generate the same operation. Yeah.
Yeah.
So, but if you keep doing that, you get worse and worse images.
Yeah.
Yeah. It gets uglier and uglier and uglier. Okay, so we're going to do a wee bit of bitwise operating because I'm going to talk about routing. Okay, so now I mentioned routing numbers, so we've talked about like big server stuff. Now these are our servers. The IP routing process. So you guys have seen numbers like 192.168. If you've ever done home networking and you've had to try and work out where things are. Yep, so 192.168. You may have even seen things like 10.10. something, or 10.0.0.1. Right, so 10 and 192 are specific numbers in the networking which talk about a local routing system. So 192.168 is a bunch of bits. Right, because these numbers, they don't actually, so computers don't see those numbers, right? They see those as bits. And when you see the world as bits, then certain numbers look much nicer than other numbers. Right? And to understand what this 192.168.1.32/27 means, and /28 and /30, those are actually to do with the bits that are in the system. Okay, now if you want to have a look at 192 as a bit, so if we go to our webpage, right, that's the streaming, if I go escape, if you have a look at 192 bit, will it actually show me 192 bits or 192 in binary? Right, okay, so yes, so 0B for binary representation. If we go to this and we go 192 in binary, luckily Google does a reasonably good job of 0B for binary, and then it says, oh, so 192 is 1 and lots of zeros, right? Because that's, so from a binary number point of view, that looks pretty good. It's like the two first ones are on and the rest are off, right? That's nice and easy to remember. And you know how we're talking about Simon and seeing the hexadecimal values? So if you do S in binary, okay, it's not gonna, so S binary character table. If we look at this binary character table, one of the neat things that you will notice, if I make that slightly larger, so what do you notice about the binary representation of the little character A and the large and the capital A? What's the third letter is off in capital and on in lowercase. And what do you notice if you just look at after the first three binary numbers? What do you see at the back end there? A is 1, B is 2, C is 3. So you know how we told you that, A was 97 and A was 65. No. A is 1 plus 64. Right? So A is 64, because that's a single bit up here, plus 1. That's why it's 65. Because it's 64 plus 1. And it's 97 because it's actually 3, right? 1 and 1, which makes 96, because it's 64 plus 32. 64 plus 32, plus 1, plus 2, plus 3. So the reason they did this is if you want to go from lowercase to uppercase, or rather from uppercase to lowercase, because when I started, a lot of the manuals were entirely in uppercase because they only had 6-bit characters rather than 8-bit characters. So you didn't have space for lowercase characters, so you just did everything in uppercase. And then they went, oh, we need lowercase letters, so actually we'll make it easy to translate between them because we'll have the case, whether it's a capital A or a lowercase a, as a single bit. And we'll have it at 32 because there are 26 letters. So we can't have it at 16 because we've got more than that number of letters. So we'll put it at 32. So we've got room for 16 characters. And then we'll just put random stuff between the end of 90, Z, and the start of lowercase a, 97. So there are a bunch of random characters in the middle there. Just randoms of whatever they felt was fun to have at the time. So this is bitwise operators. It does mean that I can do some of the rudest piece of coding that you'll ever see. Right? And so, this beats anything that Froda does, right? This is obscene piece of code. You bit shift between you do a 2 upper function, and I'll put it over on the whiteboard, and then I'll do it in code. So I never ever want to see any of you actually write this piece of code, because although it is short, right, and I can show it working, and it's horrendous, but it is incredibly short, but it's also incredibly rude. So you need to know a bunch of bitwise operators. You guys did some bitwise operators in the math, right? Okay, so that doesn't work at all. What does that operator mean bitwise? You don't know. What does that operator mean? Or. Yep. And that one? And. So when you have 2 of them, it's logical and, yeah? And when you have 1 of them, it's bitwise and. Okay. So let's take uppercase A. So 0, 1, 0, 1, 2, 3, 5. Right, so that's an uppercase A. So to turn it to a lowercase a, I need to do an and, or rather an or, I should say. So I need to do an or operator, which is the bar, so it would be this ORed with that. And that would give me, go from lowercase a to uppercase a. So if this is equals, so character equals that, then I can actually do character equals capital A, or, now, depending on how you write this, right? So if you write this as 2, 0, you could actually do 0x 2, 0, which is the hexadecimal value of this character, right? Because it's 2, 0. Okay? Now, you can go slightly shorter than that, because if you look at, do you know what character is sitting at 2, 0? Well, this is 8, this is 16, this is 32. So what is 32? What character is 32? What thing is it 32? It's a space. So I can actually do ORed with space. And because OR is one of these nice pieces of numbers, because I can do OR equals, I can write C OR equals space as my two lowercase operation. Ugly, 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 ugly. If you want to be, so you can be potentially slightly more confusing by also doing 1 shift right 5. Because you guys are used to this operator being a cout kind of operator, right? You're not used to it being a bitwise shift of a value. So I can take a value, I can bitwise shift it up 5 to where I need it to be, and then do a C OR with that. Now I can do 2 lower by doing C and equals not 1 shifted 5. Because with and, if you want to take something that has, so I rub it out, don't do that. If you have something this, which was is now lowercase a, right? And I want to turn off this bit, how do I turn off that bit? Well, I take this number, I use not of it, so I go 110, 1111, right? So I invert the binary, and then I do an ampersand logical and with the inverted. So I do and will give me 0, and will give me 1, and will give me 0, and will give me 0, 0, 0, 1. Right? Because I do a bitwise and with every single value. Unfortunately, in networking, we do this stuff all the time, right? Because we worry about space, we worry about bits, we set bit flags, we use 192, sorry, 197168. Oh no, not 196, sorry, 196.168. Was that what the... 192, not 198, 192, 168. But you see, 192, why can't I just do 1, 1? That's the number I mean, right? I mean that number. Because that would be easier than having to remember what decimal number it is. I remember the bitwise sequence, right? And so it actually is quite interesting to think, okay, if we're going to be talking binary, then we need to start doing binary operations. That's why I never want to see you guys write binary code, because anyone else reading ampersand equals not 1 shift 5. So, see, yeah, no one's going to understand that. Or at least not unless you're a networking person. Networking people will go, oh yeah, I know what that does, right? Because that's what networking people do all the time. So if we have a look at here, let's have a look, and I'll go back over there. If we have a look at these numbers. So we have 192.168, 132, right. So, again, the reason why these are odd numbers is because we have 192, 1, 2, 3, 4, right, so that's 192. 168, someone tell me what 168 is. So it starts with a 1. So this is 128. So how much do I have left over from 1 to 8? 40. Okay? So I'm going to be not 64, yes 32, not 16, yes 8, not. Yes? Is that right?
Is that really easy to remember?
Is that 168? Yeah. So it's 10, 10, 10. There it is. Huh? So that's 168. And then I've got 1. And then 32. Okay. So that is this number here. Now what does the slash 27 mean? So in networking, this says, okay, this bit is your network address. Okay, so this is, And the 192 is a local address space. Mask. It's a bit mask. The 27 is a bit mask telling you how much of this number, starting from this end of it, is being used to be the network and how much is it is local. Right? So if we have a look at the network mask, 27 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Ha-ha! Right. So what that says is I will have in my system, this will always be the same. That will address the network locally, right? So that's everything addressed with that will be local to me. And I only am allowed to have network addresses up to 5 bits, right? So I could have at most 32 minus a couple of bits probably. So about 30 local machines, right? So if you have a network E here with a /27, right? What it's saying is that this machine will have a number up to this point, and that's why it's 32, because that's probably actually the router. That's actually machine 0 in the network E, right? Because it's got the 0 left over. It is this subnet will allow me to have 32 machines on it. So once your home router gets to 32 machines on your home router network, it might just go, nope, sorry, you can't add more machines. I'm not going to serve more than 32 machines. Right? So sometimes your router will say, you know, like there's a limit to how many machines can connect to your wireless. Right. Well, it may beep or it may give you an error message saying, you know, unable to connect. So this 27. Now this 30 for this internal network here says, well, actually, we can only have 4 machines in this inner server cloud, right? Because it's using 30 of them to be the mask, right? To say, well, that's 30, there's very little left over. So I've got very few addresses in this internal space, and I have more addresses on this one. Network B here has 27, this is 28, this is 28, right? So these are internal to these. This is a separate network with these addresses, right? So when you send something to this network, the last couple of bits here will tell you which one it is, right? But you won't be able to you won't be able to have a lot of machines all with that address pool, because the mask says, no, we only address things they only have local addresses for these last few bits. Okay? So we do a lot of this network masking, and a lot of this is about like how you subnet and how you decide to send information from one place to another. So in the old days, we used to use that's classless. We used to use class-based systems. So in the old days of the internet, first internet stuff, this front number would tell you where in the world to send the packet. Right? Now MIT got one of these domains. Right? So MIT itself got, 1/256th of the internet was allocated to MIT. Right? It's a little unfair, right? But what it did is it used that number, so a router would get a packet come in with its IP, when we talk about address, like the source and destination, you get an IP dest, it would come to a router, the router would look at its lookup table and say, oh, all 32s go off in that direction. So it's everything with 32 off in that direction because that's where everybody with 32 live. Right? So it would route just based on the top. Right? But that's not, so just routing on the top end is not going to be great, right? Because once you run out of space and you need to share out IP addresses, you might have different blocks of this. This no longer means North America. Right? So if you look at the IP ranges you guys have at home, most of those are Norwegian. Right? You can actually work out location from your IP address. And that was because they used IP addresses at those big things. Okay, Norway will get that range of IP addresses, Sweden will get that range, Denmark will get that range. So they thought of them like phone call numbers, right? But once you get into kind of, oh, we're running out of space, Norway doesn't need as many as Sweden, because you've got fewer people. So we need to start eating some of Norway's allocation and giving it to Sweden, and then it no longer means where you are in the country, and so we start saying, we can't use just those heavy bits at the front to tell us exactly where to route things. And so we need this classless routing table. So, within this network, anything that is up to here, I will deal with. Right? So I explicitly tell you how many bits I know how to deal with. Right? So I'm the host for everybody with that address up to that point in this local area, and anything else send to me, because this is the mask, the 27 bits that tell you that I will deal with it. Right? So this one deals with the 27, this one deals with a smaller network, this is a tiny wee network. We're saying we've only got 4 machines that can ever have on this network. I know about addresses that go up to that first block. Right? So what we'll do is we'll take a little break now, and we'll come back and we'll show you some coding on this stuff. Do you want to see some coding? I put some code up on the repo, so you can download the code yourself and start playing with it. And we'll start playing with some code on TCP and bitwise operators. Okay, so take a 10-minute break, 15-minute break, and we'll see you back shortly. Yes.
Action queuing is as in queue the actions that the player is trying to make
Yes.
in between animations.
Yes.
Is it normal?
There are a bunch of standard processes for how you do that. Yep.
Because we were talking about glitches in games. I remember in Dark Souls 3, you can make some really fun things happen by queuing actions and then doing other stuff that interrupted those actions. And you can get into people's boss rooms and all kinds of fun things.
Yeah, no, queuing actions is something you do, particularly when you've got lag and you've got to deal with things and the server gets out of sync. So you queue actions. And
Right. I think it does it by default though for some reason.
So
Because it seems like a vulnerable system because there's hundreds of those. Like in its lifetime, there's been hundreds of exploits of that system.
it is the way they dealt with the fact that they would have network lag. So they did a queuing system, and that has its own challenges.
Yeah.
So, you had a question?
For the third year student, this is supposed to be a repetition of the networking course.
It is, because you did the cloud course that is the third year course. So this is mostly repetition. I'll just be doing some programming. So yes, but you guys no longer have a networking class. So yeah. But I was going to do the NAT a little, and in a wee bit about so I've mentioned the NAT and network address tables, and taking these 2 machines from this address space, go to the router, which is the one, and then that. And then I was going to go over to my code and have a look at TCP. And so I have this is connecting to my GTL server, which is an Apache server, and so this is using SDLNet sockets. So I open a socket and talk to port 80, right? And I get data back from port 80, and then I can do stuff with the data from port 80. So stuff you've probably done in the networking course. Did you guys? So you didn't. Okay. Well, so the idea here is that I can I could scrape web pages, right? So in my code, and what I was going to do is so the next bit I was going to do is go in here, go to my client code, and say, okay, well, let's look at this client code, and bring out your computer if you want to just sit and work, right? And that would be fine. So here I actually do that accessing. So I actually have, let's have a look. Yes, yes, more and more compressed. So here you can see I actually do a WebSocket received, printf received message in. So I think I've got that right. So if I'll just check that I'm actually doing that. Result string. Actually, that's not there. It's in this bit of code here. Result string there. Yeah. So basically, what you do to is you have to do. It's a little annoying. You have to do this bit, right? Yeah, so you create an O stream, and you do request stream get address string, and into that you pass in HTTP1 host name, connection close, and user agent, because the header. Yeah, you manually write the header in C++, right? And so you pretend to be a web browser, and you can put anything you like into the get, but also you just get a string back of the web page. And so you then have it directly in your C++, and you can start deciding.
So it's more like a text there before Wireshark.
Yes, it's a text dump of the Wireshark entry, but it's directly into your code, so you can start actually coding.
So this request say the request.
Yeah. What we do here is I'll actually, let's see. So I've done the TCP open. I actually grab, because I want to move this out of. I don't have to move it out of here. But yeah, so what it does is so yeah, what we'll talk about is you push that as a coder, you push that into the packet header. You then set a request length. I set length as request length +1. So I do a request string stream, and then that gives send request C, and I do SDL TCP sent. So SDL TCP receive, this line here, that TCP receive line gets the response from the web server into a buffer, and you just check if we've got bytes back, then that's good. And when we have bytes back, you can show the result.cstring, because it's a yep. So you do this line here, which is standard string results equals response. Immediate that turns it into a string, and then I do a straight printf of the string, which is why in here I get response and then garbage, right? And the reason I get garbage is because I didn't null terminate the response, because the response you get back isn't null terminated, right? So you have no zeros in it. You just get. So this was whatever garbage was in my memory before I put this received packet into it. Right? And then from that you can then process your string in standard ways, right? So you do, I take my result stream, so I create a result list, which is a list of scores, because this is a high school list, right? So I create a list of scores, and I take the in stream and I create an individual, and I then put the stream and I feed it directly into the position, and if it's not in the stream, is not false, then continue, and I go the stream score, so put it into score, and then put it into, so put a name, put it in score, and then I print out position, name as a Z string and score.
It's probably easier not to repeat it.
So yeah, but no, so that's what I'll be doing. So you can either stay or leave, but I'll be going into programming. So. But I need to test something. So while you guys go on, I'm going to test pointing at a different server. Yes? Why do I use end of file rather than good? Because I'm a C programmer and I've always used end of file. Sorry, I have bad habits from the old days where. Yes, it would be better. Yeah, I'm old school, and I get it wrong. So let's see what I'd like to do. So what happens if I do www.ntnu?
What happens if I do this? I know what's going to happen if I do this.
Okay.
Going by
By the minute and say, well, I've not done this bit before, so let's just see, what does this do? Haha! I've done lots of bites before. That's why I'm still alive, because I eat. Aha! It did what I thought it might. It gave me bad requests, and it asked for a bad request. Your browser sent a request that the server did not understand break ph body NTNU port 80. So it did what I thought it would do if I asked for a bad request from. That's nice. So yes, you guys can do that as well. So if we. So GTL will understand my request, but NTNU won't. But I can then start. This is a way of scraping web pages in C++. So it's going to be fun. But yes, okay. Oh my god, I've probably lost connection entirely. Let's ask for a free new position of the player for the shipping and he's giving it full network. And so lag, beautiful network updates, and then start getting these, like the last two plus the next one. So that's a way of getting at that kind of what happened when you miss one of those in a dropping A packet without and yeah. So being seen. Yep. On the gaming course, we don't have Teams, we have so Teams usually come out later. Why what would you Metroidvania. That would be an odd theme. We could do that for free theme. Do you guys have access to the repo that has this code in it? There is a GitLab repo. You guys have a look at the GitLab repo. Did any of you look at the GitLab repo? So I didn't encourage you to have a link to the GitLab repo that you registered to and put issues on. Do you remember that vaguely? There was an issue repo. Go to the issue repo because I put this code up in the issue repo so that you could download it and play with it yourself. Yes. And I have to say sorry, I thought I was the first person to push code, so I did the dirty thing of saying hash 1, and then I went to write the issue, and Murray should already used hash 1 for other issues, and oh god, I'm now getting embarrassed in front of the students because I did exactly what we told them not to do. It is make the issue first, and then change the code. But if you go into the code, well,
I don't have to leak it.
so it didn't upload the Okay, right. Right. Okay, so it's been about 10 minutes. You had a wee break, and we've got a little bit of time to finish up doing some coding and doing some network coding. So, last time we had a look at UDP, and we were sending UDP, and I was typing numbers, and you realized you had, you know, I pack bits. All right, yep. So I'm at 200. I can go to 200 and. No email about GitLab? How do you other guys find the GitLab? Okay, so it's on the it's a link from the discussion in Blackboard. In Blackboard, there should be in the discussion. There should be a link to. Oh well, it's an issue tracking form. So it's not a discussion form. It's an issue tracker. So GitLab is like Bitbucket, a repository for storing code, and you can write issues related to that code. So if we go escape, and I go to GitLab. Oh no, that's the internet GitLab. I need to get the local version. Prod 3, and. I don't know. So in this location, prod 3 Marish, we now have this commit, which has this code in it. The README, I don't know if I'd trust. It's empty. So I need to update the README because I was doing this last night. Okay, so. I have on my on our server a GTL server which has something called display. Okay, let's actually find display core game 42. Okay, so I can write into my browser. Right, so if you have a look in here, GTL/display score.php game ID equals 42. I actually have oh, you not get in.
No, it's
it's the browsing is not getting any images, right? So this actually is a high score list for some of my students, right, where they can register and they can push scores to this high score list and then ask for a list of scores and they get a list of scores back, right? So it's just a web page. It generates. Number 1 is Simon with 6,000. Number 2 is Jacob with 5,200. There is also game 4 is one of the games. I think game 5 has a few scores in it. So, you know, there are some scores. These look relatively fake. And I was able to do various things with my PHP to do things like ampersand from equals 10, which would give me the 10th highest score. And then I could do and num equals 2, which would only give me 2 of scores, right? So it'd give me from number 10 for 2 scores. If I ask for 20 scores, it'll give me up to 20 scores, right? So this is a server that is running, giving me high score lists. Now in code, I can say, okay, that's my GTL server there. I put in the address stream. So here we're going to do a whole bunch of C++ stuff. So we have this address stream, and it is, I've given the host name as gtl.heg.no, and then I create an O string stream, so it's going to be a stream of strings, and that's the address stream, and I pass it my display score PHP, game ID 42 in this case, and from equals from pos, and num equals num scores, which I am getting from this function up here, pull high score list. Right, so I created a pull high score list, and I passed it the list that I want the scores to come back into, which is a list of a class called score, which I created, a struct called score, and two numbers, the from and the number of scores I wanted. So I then do an SDL resolve IP, which came from, so resolve into something called an IP, which is this IP address. Right? It does the IP, I put into this thing host name as a C string, and 80, which is maximum characters. So it takes host name, which is in this case gtl.heg.no, and it puts it into and resolves that as an IP address. Right? So it solves does a DNS lookup. If it finds it, it continues. If it doesn't, it crashes and returns false. I then do an SDL TCP open. So I tell my socket to open a connection to that IP address. And this is 80 is port 80, I should say, rather. So that's host name and port number. Web ports are port 80. Right? So that's the local lookup for saying, hey, what kind of communication are you? So that's port 80. I then do something which looks a bit odd, but is the, again, an O string stream, and I do the request string stream, and I send into that the word get with a space, followed by the address string, so this address stream that I wrote up here turned into a string, right? So this address stream here I created. Right, so I've connected the IP address. I then use the address stream to send it in here to say get this thing plus HTTP 1.1/n. I am manually writing the HTTP header to pretend to be a web browser. Right, so I have to say I'm a web browser, honest, you should give me data back. Right, so I put in HTTP 1.1. And then I say host, and I use my host name to say, hey, I'm coming from here. Right? I could be anywhere, but just tell it where I'm hosting from. And I tell the connection to close, which means I'm not going to hold the connection open. I'm just asking you to send me data. Right? I'm not going to try and hold open a connection and do a Ajax JavaScript-y thing, right, with open connections. And the user agent is get HTTP 0.0. with 2 end of lines. That is enough header information to make the Apache server go, oh, you're a browser, I'll give you HTTP content then. Right, so having done that, I take that request string, I take the stream, I turn it into a request string, a standard string, right, because that's currently a stream and it doesn't like streams. So I get a string. I take that string and I create a length is the request string plus 1, unfortunately, because I need a padded bit at the end. And then I send the C string of the request as a void pointer. So I just send the raw data to a TCP send socket, right? So I take a TCP and I send that string I constructed, right? Which makes me look like I'm an HTTP, I'm a browser. So I send that in, and if I get an error, it then prints out what the error was and exits. Right, so that is setting up to send via TCP a request to a browser. I then set up my response. I say, okay, I'll take a 2048 buffer, I'll make a character response buffer of that length, and I'll take bytes, and I'll receive a bunch of characters back. And so I do TCP receive, saying, hey, I sent you this, I'm waiting for stuff to come back. If I don't get anything, then I say, that was odd, I should have received something, and exit. Then I go into, I turn the response that I got back, this response thing here, I turn that into a string, and then I print the string. Right? I do a printf of the C string. So if we have a look at how that code actually looks, when I go, now if I go with this and I close that one and I build, dun, 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 and I build and run, building, running. Okay, so what I get here is from the result string that you see up here, which is what I printed here, result string, space, and then a %s, and I get HTTP 1.1, 200, okay, you're a browser, I'll give you data. It tells me the date that it sent me in text. It tells me that it's a 2.215 Apache server. So if I know I've got vulnerabilities on that, I could use that. It's using PHP 5.33. It's sending me 133 characters of stuff, and the connection's going to close, and it gives me the text HTTP and the character set. And then it sends me data, and then I get to this point, and then I get all of this garbage. The reason why I get that garbage is because what I did here was I did a %s on a character string. And non-null terminated character string, because there wasn't a 0 at the end, so the string just printed whatever memory happened to be lying around in the buffer when I created the buffer to put the memory into. Right? So I can actually do this little dirty trick here, which is my response bytes. So if you have a look here, I say bytes equals the TCP receive, which is the number of bytes that TCP received. So what I can do is I can go in here and set the byte at that point to 0. And so when I do the string print, it'll go, oh, null terminated string, and I'll stop printing at that point. Right? So that's a way around that, right? So, but I leave it in there because it shows you kind of the string is just printing whatever is in memory. I can then go through and I can process that list of data I get back from the server. I can get this. I get 4, Jacob that number, 5, Jacob that number, 6, Jacob that number, right? So Jacob was playing this game and scoring many thousands of points. I then do standard C++ stuff where I can process that string, right? So I do a stream reading into score, position score and name, position score name, position score name, and then I can print those out. Construct a list of those by doing score list pushback, and then I can return true because I've pushed into score a list of the scores that I received back, right? So this high score list will query the web page, get the data out of it, and put it up. Now, you know, that's nice. What I can do, and what I was just trying before, and it's quite nice to experiment with, is, okay, let's see what happens when I change this from being GTL to ntnu dot, www ntnu dot no, and let's now, because it doesn't ntnu doesn't have a display score PHP on the root ntnu site, not surprisingly. Let's just create a standard end there, and I'll just comment that bit out. So I don't know what this does. So let's try this. So I think this will work. I close that. And now I could go back to there, go play. Right, so now I've changed my host name to the standard www ntnu.no. So that should be the home site of ntnu. So what does the home site of ntnu give me? Okay, it gave me HTML, bad request. Your browser sent a request that the server did not understand. Apache 248 server ntnu port 80. So, right. So what I did is I got my header wrong in some way. So let's try, if I just send it a slash, stop. And let's see if I need to do that. Otherwise, I'm going to have to search for it, right? I'll have to search for what I'm missing in my header. And you can actually go to various pages that will tell you what you're missing in your header. Nope, it still doesn't like me. It's still requesting, but you can see here it's responding with a web page, right? With a 400 bad request. If I go to the web page and go www.ntnu.no. Right, so what I should be getting is the source back from this. So if we have a look at inspect, right, what I need to find is how I get this big doc type. And it'll be because my HTTP header is wrong, right? I'm sending the wrong request. So if we have a look at, so it's using a different Ubuntu Apache version. And so what I need to do is go HTTP header, and we go into here and we start asking for oh, it's sleeping. Right, so so here if you go and have a look at the HTTP header list, you can go and find the HTTP headers and file names and values, and you can see what the field requests are. And so, oh right, so maybe that's what I was doing wrong. I wasn't, so what I had cut out that I wasn't supposed to cut out was that in here I was doing get and a des stream and HTTP 1.0. So I need to actually do a get of something, right? So if we have a look at the web page, we should be able to find get request types, get. So request method get, and it should be web applications C safe methods. So I need an example of a get header. So show me the example of a get header. Okay, let's go. Example of a get header in HTTP. Oh, HTTP. So header fields, tutorial points, requests, HTTP protocol headers. Right, so except, for example, encoding, fields, example, authorization. Right, nope, that didn't help me. So this is basically the process by which you try and manually work out what the header is to send to the right location. I'll just see if I have in here the address stream. If I go and look at this address stream and say, well, actually what I was missing was, is there anything I was missing from here that it should have had? Assuming that that should be okay, and then that would be okay, and then get errors, get the address, host name, connection close, actually get. So we'll stop that and run. So the main point here is once I've fixed this code, I'll send it to you guys so you can play with manually scraping web pages. It works on my web browser, but it doesn't work on the NTNU web browser. So the NTNU web browser is saying, hey, I don't understand what you're asking for. If I point it to another web browser, where's someone else that you guys know about? Another location? Anywhere? I wonder what Google will do. I have no idea what Google will do. Let's see. So if we browse that and have a look at what does Google do when I try and connect to it with a request. Right, so 303 moved. So the document has moved to so it's given me information. Oh, you can't just request that. I actually moved you to google.no and this long thing here, right? So it gave me a a 302 found private content private cache, connection close, and header moved and 3 moved, and click the document and move to there. So let's try enter.new.no and stop. Now, of course, if I was doing this, rather than recompiling, because I'm using a host name here, I should have a string stream coming in that I can just type in random URLs, right? So I wouldn't have to recompile each time, because it should be an input character. Ooh, that's interesting. Right, so it now gave me cookie information. So it's got that set cookie information there, and it's got an address, and it's got accept, and then it's got the HTTP item codes, and Velkommen til Google. Sick. Finde letter etter på nettet på en blank. I think it's around a blank web page, yeah? So then description meta nude name. Why have you got content nude p? Nude p. I don't know. But meta content, and then it gives you a bunch of information, and then images with Google standard colors, and then a bunch of numbers. And because my buffer basically runs out after the end there, I just stop, right? And it just goes, oh, okay, I've had enough now. So as you can see, I've got something from Google. So what the idea is here is that you guys can program, and this is TCP networking. I've just talked to port 80. If you can find it, if you guys know of another port that is open, a TCP port, and so you could talk to other 8080s which were TCP. You just need to know basically the protocol of how to talk to it, right? So the protocol of what requests you can make and how you send and receive and send and receive. That's the protocol. And you might have an API with specific GET messages that you can use, right? So remember we talked about an interface with the protocol? So the HTTP is the protocol of what the structure looks like, and the interface is what you can put in your GET. Say GET display score is an API, right? So this is just a standard GET request which gets the main page. So if I put in, let's try something weird. Oh, so HTTPS is a different protocol to HTTP, right? And so you might find that if, let's see, stuff.co.nz, where does that take me? It takes me to www. Oh, and it takes me to a secure one. Why do you take me to a secure? I want to go to non-secure. No, it just keeps redirecting me to the secure pages, right? Anything that requires you to log in uses HTTPS. Can you think of a website where you can't log into? Most of them have logins now, right? They want you to give them data. But I think if I try that... Right, GitLab's not secure. Yeah. Well, that's because it's local and we didn't secure it. So, yeah, we didn't secure that, so that's our fault. But HTTPS requires you to set up much more header information, right? Because you have to set up a token and those sort of things. So I'll try seeing what happens when I go to stuff. It'll probably redirect me and say, oh, we've moved. Oh, it's still running. That's why. I don't think I need to do that. So, why was it still running? Now it's exited. Yeah, now it's exited. Okay, so let's have a look. What did it fill? It didn't fill the buffer with. All right, has moved permanently, right? So the 302 was saying, oh, no, we're now in secure. You have to send HTTPS, right? So this only works with non-secure websites. If you want to do secure websites, then you have to do, and if we go to Google, we can go, so secure HTTPS protocol. No, it doesn't. It has to force everything. I think if it can find the HTTPS version, it will give you the HTTPS version. Right. Yep. On whatever you've got. So so you'll find people who are doing this, and with secure sockets, you then have to do a whole bunch of SSL and additional things, and so secure requires more work. But the idea here is that you guys can write, and you can write code that connects to web browsers. They're just a server, they're just a network port, they're just an IP address. You ask them stuff, and they give you stuff back, right? And if you can work out the protocol that they're using, then you can work out how to get whatever information they're sharing back, right? The first Java program I wrote was a networking program. I scraped gambling websites looking for odds to see if I could ever bet and always be above 1. Right? So you'd like bet for New Zealand and Australia, and for Australia and New Zealand, and for Sweden in Norway, and for Norway and Sweden, because, you know, people are emotional, and you see if you can get odds on the sporting event where you can bet $1 million and end up with $1,010,010, no matter what the result, right? And the closest I got was 0.99. So from that, I decided that gambling companies were probably doing this already and working out to balance their odds so that nobody could actually do that to them and end up just betting massively across multiple platforms to always win, right? So yes, I had hopes, but yeah, it didn't work. But that was doing this process of going to pages, opening sockets, saying, hey, I'm a web browser, give me information, and having them give you information. Right? Now, legal? What do you mean, is it legal? I'm just browsing public web pages. I'm not faking anything. I'm not breaking any of the rules. You could argue that your no robots text, right? So you guys know in web browsers, you can, like, if you're on a web page, you can set no robots, which is a kind of request for people who write scrapers to not scrape your page. Doesn't actually stop them. It just says, hey, please don't. And if they choose to, they will anyway. And so, yes, you can scrape whatever pages and create your own web browser, right? And actually, if you run a web service, you'll find that a lot of the hits you get on your web page come from web spiders written by university students and just all over the world who are just randomly wandering around pages grabbing content. Right? Because that's what you can do, right? There are some universities that had this as an assignment, which is write a web spider. And in C++ or Java, you go around and you just scrape a bunch of web pages and extract content from them. Right? So yeah, it's just networking, and you just use here. You can see host name. This is localhost and a port number 5000. Right? And the low ports are all taken up with important services, and you can look those up. Port 80 is generally browser. Higher ports, whatever you like, right? Random things are up in higher ports. And often you can open up your own higher port. So, do you have any questions that we should try? I'm sorry, I can't do secure networking in the 10 minutes before we're finished, but we could certainly look up something like SDL net secure HTTPS. So there may be someone viewing this with, can you do SSL? Yeah, so there are people talking about, I'd love an SSL tunnel for SDLnet. So yes, so you can do SDL tunneling. There are various ways of setting up SSL, so secure connection to a browser, to a web server, and do that connection that way. But yeah, it requires more programming to scrape those. Any other questions you have?
I do have like a website that doesn't have HTTPS.
Okay. Give me a website without HTTPS.
It's a legitimate thing. It's not something stupid. I literally took the first thing I found. Like, I can show you the page if you want. Just
Next.com.
It's this. It's not.
Yeah, no, it just, like, the initial title just looked a bit... Could that be some... me in sex. Which, yeah, well, I'm trusting you here. Let's see, what does... Aha! That looks more like a full web page. So, without an HTTPS redirect and saying, hey, 301, I'm not here, this says HTTP OK, excellent. And so what I got was a doc type and some language and class information, and in the title, CMEX, and a favicon icon, and all of what you would expect to see, even like if LTIE9. So if you're Internet Explorer, do this thing, otherwise these are the CSS styles. So you can see through, that was, and up to that point where I stopped because my buffer ran out, right? I just, instead of having a 2048, I just make, 5,000, 10,000. I just make it very large. That would be that's getting a standard web page. And now I could start scraping data. Right?
Would you scrape data? Like, what data would you get and what would you use it for?
Well, that's why you try and work out what pages you want. I mean, YR, for example, right? So you might want to show your own weather data. So you could write a web program that would ping YR, get its weather data, and show it to you on your mobile app in some way, right? Or you could be storing it. You could have it run as a cron job. You could send data to things as well, right? So you could have post data where you post to the web page information. Yeah? So there are lots of ways you could do this. But just being able to do networking and being able to see that the web is just a socket sending strings back and forth. That's all it is. Right? And so networking is just understanding how to get access to things and understanding those protocols. But for most of them, you just look them up and you can find them, right? You can find the descriptions. Okay, any other questions? So the session at 4 o'clock today is for all of you who were struggling with the first assignment. Mariusz will be around helping people understand the first assignment and making you ready for the second assignment, which follows on from the first assignment. So if you have any questions about the first assignment at 4 o'clock today, Mariusz will be around helping you all out with that. And any other questions you had around the first assignment, particularly if you had any errors or if you uploaded the wrong thing and things weren't working, come and talk this afternoon at 4 and he'll resolve all of those issues. And if you had absolutely no issues with the first assignment, you could come along and just watch gloatingly. Though I don't think there are that many people who would do that. But yeah, so no, do come at 4 if you need any help at all. Okay, Mariusz will see you at 4.
Should I ask for help at 4? I'm planning to be here anyways to work on other things, but should I be here at 4 and ask for help? If I think I submitted correctly, but I don't know what I submitted and I can't check what I submitted.
Oh, you can verify what you submitted, so that's, yeah, so he'll show you, how to do that at 4.
Could you try to connect with that program to Google --people?